Okay, so I'll talk to you in English also. Hello, everybody. I'll represent to you today our research of reconstruction of sea state by polarimetric reflection measurements and machine learning methodology. I'm Noam Ginio. I'm a PhD student here in the Faculty of Civil Environmental Engineering in the Technion, and my advisors are Professor Barak Fishbein from Tech Lab that couldn't make it today because Tzav Shmone, and Professor Dan Lieberson from TCL Lab, and we have also Professor Micha Lindenbaum, which is fully involved in the project from computer science. So let's start with a little motivation and background. So as you all know, the wind is the predominant force in the sea, and it generates a complex and stochastic water waves field, which we all want to measure accurately. And a little basic definitions, we're talking about eta as a function of x, y, and t that represent the instantaneous surface elevation fluctuations, and its gradient give us the surface slope. And if we apply arctangents in the x and y direction, we will get this slope in these directions in degrees. And here you can see an illustration of a wave propagating to the shore. So what is the existing methods for these measurements today? There is several non-destructive remote sensing techniques that were developed over the past decades. We won't go into it in depth. It's basically the acoustic method is the ADCP and the pressure gauges and various radar techniques. And in the photometric, we can find stereo imaging, and the LIDAR, which basically all suffer from significant limitations due to cost of operation and some inaccuracies in the measurements, and therefore the search for more techniques is still ongoing. Here I'll present you the research that we base our research on. It's Zappa published in 2008, the polarimetric slope sensing, the PSS, which exploit the polarimetric properties of skylight reflected from the water surface to recover the instantaneous 2D water surface elevation slope field. He used a system of equation that describe the function, which is overdefined. He uses physical model to describe the water surface under simplifying assumption. And here we can see a geometric representation of the problem. Basically, the light from the light source hits the water surface and captured by the camera, represented here. Oh, excuse me. Which is represented here by the vectors A and B, which define the green plane of reflection and also define the surface normal, which we would like to retrieve. And the angle between this green plane and the image plane is seen in orange here. And these two angles, theta and phi, describe us by these two angles. We can find our surface normal. And to correspond with our work, with Zappa's work, our theta in our experimental setup is corresponding with eta d eta to dx, and the phi angle is corresponding to d eta to dy. Now let's talk about the limitation of Zappa's method. The analytical solution under the simplifying assumption of high water turbidity and purely unpolarized skylight do not hold in real life, and therefore in general conditions, the solution cannot be achieved analytically. And therefore, in our research, we aim to solve the general case by implementing machine learning. Now, machine learning in a nutshell is a computer algorithm that improves automatically through experience, and more specifically, what we are using, the artificial neural networks, the ANN, is a feed-forward model based on supervised training. The reason that we chose the ANN is because its capability that you see on the right to learn complex pattern and nonlinear relationship. It's able to generalize in noisy environments and can deal with incomplete or imprecise data. And we can incorporate prior knowledge and realistic physical constraints. Now, let's dive into our methodology. We'll start by the instruments and data collection procedure. So here you can see our experiment setup. Basically, is the wave tank that we generate mechanical waves. We put a light source that the light reflects from the water and captured by our polarized camera, synchronized by resistant wave gauges. And here you can see an image from the T-cell wave tank that we perform. You'll see the results that we performed in this tank. And here is the polarimetric camera of FLIR that we are using, that each 2x2 array of pixels is equipped with 4 linear polarization in the angle that you see in the image. And once we obtain the data from the wave gauges and the camera, we need to, because one is in the real life coordinate of X and Y, and one is on the UV plane of the camera, we need to perform standard calibration between them with checkerboard and control points. And now for our applications. This method is aiming for two main applications of laboratory and OpenSea. Due to time constraints, only gonna elaborate on the laboratory one. So for this to become a laboratory tool, we need supervised data sets like the setup that we showed you. We have the inputs that you see here on the top left, which is the polarimetric pixels light intensity that we take out from the images. And the targets, we have the wave gauge measurements that we interpolate into time series, and we feed both of these data sets into the ANN, and it can learn the connection between them.
نعم עוד 2 דקות יש לך.
Really? Okay, awesome. Now a bit about for pre-processing. So to increase the signal to noise ratio, we are doing some special averaging. Here you can see the raw image that we received from the camera with the light reflection. And here we chose a 50 by 50 pixel averaging. And then once we chose that, we select a few neighborhoods that we combine them for our training set. On the left here, you can see a zoom in of a 10 by 10 pixel area within the light reflection. And really quickly on the ANN, it's a feed-forward artificial neural network, fully connected in our case, with a back propagation learning algorithm of standard gradient descent, and we use the MATLAB software for it. And now for our results. Reconstruction of monochromatic propagating wave train diagonal to the camera point of view. After further processing of integration of the slope, we reconstructed here the surface slope. On the y-axis is the surface slope, and on the x-axis is the time, and we can see pretty good reconstruction of on the blue dots is the reconstructed signal, and on the red circles is the measurements, the ground truth from the wave gauges. And just to emphasize the strength of the results, here is also amplitude spectrum of the both of the signals that we see a very good correlation between them, especially in the peak of the amplitude. And some more results of this time from a reconstruction of monochromatic propagating wave, this time perpendicular to the camera point of view. You can see here the neighborhood that were chosen for the training, and two reconstruction area, one very close to the training set and one further away. Both of them gave pretty good results. So what we learned so far in the ongoing research in the wave diagonal to the camera point of view, we were able to reconstruct the surface slope of a propagating wave in a 2D plane, and the trained ANN managed to catch the orbital period and amplitude of the slope fluctuations. And with additional processing, we can also, the water surface field can be obtained. And in the perpendicular wave to the camera point of view, the ANN was able to reconstruct the surface slope. And in both examples, we managed to catch the overall period and amplitude slope fluctuation very well, while the accuracy of this instantaneous value varies. Sorry. And thank you for the Israeli Ministry of Energy for funding this research, the Israel Port Company for helping with scholarship, of course, the Technion and the faculty, to Sagi Knobler in my lab that did this research prior to me, and of course my lab members and advisors for all their help. And thank you for listening. And